prediction. If the rank of this, as I said before, the rank is either n or n plus 1. It could not less than n. Okay, so suppose the rank is not n, then it must be n plus 1. So our F is a map from delta neighborhood of x0 to Rn plus 1. So if the rank of the derivative at x0 is n plus 1, by our previous theorem, the point fx0 is interior point of the image okay. This is y0. This is y0. This is an interior point. So there is a delta positive, maybe epsilon positive, such that the epsilon neighborhood of this y0 in Rn contained in this this is by the definition of interior point. But fx0 minus heart of epsilon 0 belongs to y0. Y0, what's y0? Y0 is here. Y0 is fx0 0. Okay, y0 is here. So the distance from fx0 to 0 is the same as the distance of y0 to 0. Okay, so sorry, this is n plus 1. I misprint n plus 1 because fx0 is one dimensional and 0 is n dimensional. Okay. Why this is true? You can compute the distance from fx0 minus heart of epsilon, this point to y0. Y0 is fx0 0, right? So the distance of these 2 points is heart of epsilon, which is smaller than epsilon. Okay, but this point is just y0. Okay, so our point fx0 minus half of epsilon 0, this 0 is n-dimensional vector or n-dimensional point. So the distance of this point to y0 is less than epsilon. Therefore, this point lies in the epsilon neighborhood of y0. But this neighborhood, in turn, you contain in the image of capital F. So we can find a point. There must exist some point x star in this delta neighborhood of x0, such that capital Fx star is fx0 minus heart of epsilon. Okay. I have no place to write. I will write it in the next page. So there is a point x star in the delta neighborhood of x0 such that our this point fx0 minus a half of epsilon 0 is the image of fx start. That fx start, by the definition of our map capital F, this is fx start g1x start, actually gx start. Okay, so this means gx start is 0. Gx start is 0 means that x start belongs to the constraint set M. Moreover, x star is a point in the delta neighborhood of x0. So in conclusion, x star belongs to the intersection of this neighborhood, which M, but fx start equals fx0 minus half of epsilon, which is strictly less than fx0. So this is a contradiction, right? The truth of the delta satisfies this condition here. Satisfies this condition here. When x is a point in the intersection of delta neighborhood of x0 and M, the value of f will not less than the value of f at x0. But now, if the rank of this metric is n plus 1, we can find using our later argument. Once our claim is not true, that is the rank of this metric is n plus 1. Then we can find the point x star in the intersection. But the value of fx star is strictly less than fx0. Okay, our fx star is strictly less than fx0. So this is a contradiction. This contradiction means that the claim is true, because this contradiction is the result of the assumption that the rank is n plus 1. So n plus 1 is not true. So the rank has to be n. Then, as we said before, once the rank is n, the first row of the metric is linear combination of the last n rows. That is our conclusion of the theorem is proved. Okay. Now we provide another traditional proof, okay, of the Lagrange multiplier theorem. The theorem says that omega is open of Rm and f and g, f is C1 defined over omega, and g is a vector valued function, also C1, mapped to Rn, and if x0 belongs to M is the inverse image of 0 under our G, and the rank of the derivative metric of G and x0 is n, then there is lambda such that the gradient of fx0 plus the transport of this is 0. So this is the theorem. So we use another algebraic method to prove this theorem. So another proof. We have already proved this result using geometric method, right? Now we use algebraic method. Denote x to be z and y in Rm minus n Rn. Then x0 maybe x0 is a point which is AB. Here A is n minus n dimensional, B is n dimensional. Actually, we assume that since the rank is n, since the rank of this matrix is n, we might assume that the last n columns of the matrix, because this is an n by m matrix and the m is not less than n, so we assume that the last n columns is linearly independent. In other words, we assume that the determinant of the partial derivative of g with respect to y at the point x0 is not zero. We make this assumption. This is precisely saying that the last n columns of the derivative matrix of G is linearly independent. So what we have? So we have G x0 belongs to M means Gx0 is 0. So this Gx0 is GAB. GAB is 0. And this determinant x0 is AB. This determinant means that Gx0 is GAB. It's not 0. So we can apply the implicit function theorem. There is a function defined near A. Maybe for some epsilon positive, we have a function. We have a function y defined in the epsilon neighborhood of A, such that ya is B and G J yz is 0 for any j in the epsilon neighborhood of A. Then A must be a minimizer of the composition function Pc. Pc is fj yz. A must be a minimizer of this function, because when they why this A is a minimizer of this function? Because when J is near A, then Zyz belongs to the M. Why this belongs to M? Because Gzyz is 0, right? Because Gzyz is 0 for the near A. So this implies that Zyz belongs to M. So Fzyz will not less than Fx0, because Fx0 is the smallest value of F at the point at the set M near the point A, x0, near x0. Okay, so Zyz belongs to M and also near x0, that is AB. So by the assumption that x0 is the constraint minimizer, we see that Fzyz is not less than fx0. But fjyz is pz. And fx0 is f a b. B is yz, y8. That is psi a. So this proves that for z near a, psi will not less than psi a. So a is minimizer of this function.